The first thing I do is chop the head off the sugar container. I'll get all the sugar out much faster this way. I pour out a whole pound of sugar into a 1-liter beaker. Then I add the sulfuric acid. It is important to stir all the sugar thoroughly as you do this to not leave any sugar unreacted. At first, it just looks like a tar blob, but soon, a black head arises. It shoots out a lot of smoke in the form of steam. It's mostly made of water with some sulfur dioxide after a bit of the sulfuric acid is reduced. Strangely, I smell notes of caramel and cinnamon from the whole thing. Once the height is approximately the same as the beaker, it is important to help direct it to get the straightest pillar, otherwise it will curve and eventually grow down. I'll also try pulling on it a bit to gain more height. Wow, now that's impressive. It's like catching a big fish. To get the residue off and cool it faster, I'm going to drop it in a bucket of water. It fragments it a little beforehand. When I put some baking soda in there, the high acid content causes it to bubble intensely as carbon dioxide leaves solution. I'm going to do this several times to neutralize as much as possible. After soaking for a few days, I'm going to put this on the grill. I want to get the water content out quick with high heat. This way, the rapid expansion of steam will open up the carbon more. After a day of roasting, the carbon is extremely light and quite brittle. When I pick them up, some residue always sloughs off. To see how good my activated carbon is, I'm going to pit it against its competitor, activated charcoal. Now, the difference between the two is that this activated charcoal has been extremely powderized. It's almost like flour, whereas my activated carbon is quite fluffy. However, despite the differing amounts you see, both of these are 7.1 grams. To do this, I squirt orange drink mix into two 60 milliliter solutions. I try to get roughly the same concentration in each. Then I put in my carbon and then the activated charcoal. I make sure to mix really well. One thing I noticed with my carbon is some fizz. I think it might be sodium bicarbonate residue reacting with the citric acid in the drink mix. To see how well it sequestered the dye, I'm going to put it in a larger solution. First, my activated carbon. It'll probably take time for it all to be absorbed. In the meantime, let's see how our commercial carbon does. Wow, that got black really fast. It's pretty much opaque actually. A day later, there is some separation, but the activated charcoal is really dispersed. There definitely is no orange color, beating my carbon there, but the charcoal is so finely ground to maximize absorption that it basically becomes a black dye. At least mine can be mechanically separated and with a bigger quantity or more time, can clear up the water much better. In the meantime, pick your poison as to what you want to drink. What we're first going to do is just pour all of this. We're going to be needing all of this for our experiment. Once again, make sure it is chilled prior to use. You might even want to do a little flash freeze an hour before you're going to actually use it. So you want to store it cold, but before you use it, you want to freeze it. What we first need is 125 milliliters of acetone. This corresponds roughly to about 1.6 moles. The next thing we're going to do is load up our syringe. Now the reason why you want to do this versus direct pour is that the acetone will tend to sit on top, superheat with the contact of the chlorinating liquid, and it will just boil off, and you're going to lose a lot of acetone. So this is why you want to inject it right into the heart of the chlorinating liquid. And you also want to make sure the acetone doesn't touch the rubber tip because it can solvate it. So you want to stir it. As you're stirring, you just slowly pour it in. Now this is cold, So you're not going to get a lot of evaporation loss, but it's still good you take these precautions. We're going to load up another shot. And then once again, with our strategy, right? Slowly pour it in. As you can see, our acetone is starting to react. Now, we're also going to add the rest of this, because I can't get it in the syringe. We're going to add the rest of this manually. And as you can see also, the green part, it was once fully green, now it's kind of this grayish green, is because the chlorine is being used up as it's making the chloroform. Now it is solidly opaque because the reaction is in full swing. To minimize chloroform loss and acetone evaporation, you'd want to put a seal over it. It's going to be kind of hard to unfold with the wind that's going on. About 30 minutes in, you're going to see our solution is very dull. It's light green, but it's not that full concentrated liquid green that you saw a while back. That's because most of the chlorine has been used up. Now, if you zoom in real close, you can see this bubble layer. That's our chloroform made. Now, because it's a 4-quart bowl, you might think this is not a lot of chloroform, but by the surface area alone, we have a lot of chloroform. Now, this is good, but I think we can do better. So, we're going to try to salt out some of the chloroform. So, we're going to start adding some salt and just see where we go with this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, that's a lot of salt. And we're just going to stir it around a bit more. Until all the salt dissolves. After about 10 minutes, we're going to see how much chloroform we have now. This will be our final amount. As you can see, the chloroform bubble in there, it's quite big, especially wide. It takes up the whole base. Now, chloroform is very slightly soluble in water, but the salting out will make sure that it's practically insoluble in water. Now, the decanting, you want to be very careful you don't lose any chloroform. So you want to do this very slowly. Now, we are at an amount where our chloroform is going to be very fickle to get out. So we have to do some extra processes in order to get this out. Now, it's very important you do all your reactions slowly because you don't want to disturb the chloroform bubble. It's surprisingly fragile and it can easily go inside the water solution. What we're left with after our hard decantation the first time is this thin aqueous layer, and then we have our chloroform layer. As you can see, they're very close together and stuff, and we don't want to lose any more chloroform. So we have to find a way to get it out with the least amount of aqueous liquid. So we're going to try another method. Let's try to scoop. As you can see, we have a big chloroform bubble in there, but we also have our aqueous layer. So we have to allow this to rest for a bit. That way all the bubbles can reconstitute into a big bubble, and we can slowly pour off the aqueous. After we decanted most of our solution, we still have our chloroform bubble in a little bit amount of aqueous liquid, but we're going to process that later. So we're going to pour this into our little storage unit. And then we're going to set them aside and do it again. After doing our extractions and decantations, we got roughly a little over 100 milliliters. So we're not done yet, we're almost done. Right? Look how crystal clear that is. It's highly refractive, as it's been known to be called. We're going to just put in a little bit of anhydrous magnesium sulfate. This will dry out any water that the chloroform solvated. And we're going to shake it around. And you're going to see that the anhydrous magnesium sulfate doesn't even dissolve. That means we have pure chloroform in here and we have no water at all. All the water has been sucked out by the anhydrous magnesium sulfate. Finally, we're going to bottle this and put this away for future use. Make sure you don't get any magnesium sulfate in there. And you might be able to notice the little water bubble that is surrounding the magnesium sulfate. So we don't want that in there, so that will be enough for a decantation. And just like that, we have made chloroform. We actually made over 1 mole of chloroform because of the techniques that we used. To make the polyphosphoric acid, I'm going to start with 750 milliliters of phosphoric acid. The next thing I'm going to do is weigh my crucible. The white staining inside was from other attempts, as this is my dedicated polyphosphoric acid crucible. Next, I'm going to weigh how much phosphoric acid I'll be using. The weight is right at 1,222 grams. Then I'm going to place it on my hot plate, wrap it in heavy-duty aluminum foil to insulate, and give it a big hood for further insulation and venting. Sometime while I was away, the crucible actually broke. I heated it incrementally by increasing the temperature 100 degrees every hour until it reached 400 degrees Celsius. I've used this strategy before, so I'm not sure why it broke now. The only explanation would be I used traditional soda-lime glass rather than borosilicate used in Pyrex and lab glass. Repeated condensations must have weakened the jar up to now. Obviously, the phosphoric acid positively totaled my hot plate, so this won't be used anymore. Around the base, I had to put down some sand to limit the spread of the phosphoric acid, but ideally you should use kitty litter if this happens because it is designed to be absorbent. This time, I weigh a 1 quart Pyrex glass. It is right at 590 grams. When filled with 600 milliliters of phosphoric acid, the weight of only the acid is 972 grams. You may be wondering why I'm using less, but really it's because this is how much phosphoric acid I have left. Next, I place the Pyrex cubicle on my old trusty hot plate. I insulate it with sand this time to really allow even heating. Then I'm going to turn it up to 11. Lastly, I'm going to cover it with a pie hood. This hot plate, though small, can still go up to 400 degrees. I'll leave it like this for 40 hours. 20 hours later, let's check out our product. As you can see, there's a nice layer of polyphosphoric acid on the bottom and some large flakes precipitating on top. There's still a decent amount of phosphoric acid though, so I'm going to let this continue for another 20 hours. Sometime later, when I went to check out my polyphosphoric acid, it was mysteriously stiff even with the hot plate at full power. It turns out I completely burnt out the motor. Even at full power, the plate is completely cold. So, I get a conventional cooking hot plate. At full power, with the coils red hot, my polyphosphoric acid becomes runnier than skim milk. I can easily stir it with zero resistance, but be careful of flicking any droplets. It could scald you big time. When cooled, the polyphosphoric acid is a lot more stiff and paste-like. The only thing left to do is weigh it. The final weight is 1,333.5 grams. Minus the bowl, the total weight of the polyphosphoric acid is 793 grams. This means our acid lost 176 grams of water, 145 of which was free water and the rest as part of the polyphosphoric acid molecules actually condensing. The first thing we'll need is 280 milliliters of ammonia. We're going to keep it like this, and then for this one, we're going to just fill it up to the 200 milliliter mark. This equates to roughly 4 moles of ammonia. So we're going to add our ammonia in this big bowl, and then we're going to add 450 milliliters of formaldehyde. This is roughly 6 moles of formaldehyde. Now, because this is a condensation reaction, it's going to get a little hot. It won't be like a steaming, boiling sort of hot, but the reaction will get very warm. Like that. Now the reaction is already pretty warm, so all we're going to do is apply gentle heat afterwards. We want it to be able to slowly evaporate this to minimize sublimation. So I'm going to have it around half and just heat it there for a while until I just get the powder left. After a few hours, you can see our liquid has become a fully fledged powder. There's a little bit of that orange, yellow stuff. I suspect it burnt a little bit, but for the most part, we got a lot of powder. The total yield was 98 grams, so that's a little bit around 42% yield. I suspect it's because of excess evaporation, but this should still be enough for the next part of our experiment. So to test how hot this is going to get, we're going to have some things. First of all, a sausage. I'm going to wrap this guy like a tinfoil dumpling. Right? And we're going to see how well that cooks on the side. I'm also going to have a boiling flask with some water in it to see if it boils. That should be about a good amount. I'm also going to have a bundle of sticks in here to see if it can burn sticks. And lastly, I'm going to have a titanium cube. And we're going to see how well that burns too. Let's fit him right here. Now we're going to light this guy up. As you can see, we got a little fire going. Maintains pretty well. It's going to spread, so I'm going to put this thing on it and we're going to see how well it spreads. Pretty soon you can see how there might be some condensation at the bottom of the boiling flask. See the fire? It's growing a little bit. It's getting bigger. It's definitely getting bigger. Maybe we should have added more hexamine in there, but we'll see how this goes. You might be able to hear some sizzle going on. That's because the fire is really starting to ramp up. It might be because of the sausage. Let me see how hot this tinfoil it got. It's quite a bit warm. It's definitely hot. Yeah, the glass is pretty hot to the touch. You might be able to see some vapor in the boiling flask too. Let's see if you see some bubbling. I thought I saw a bubble. Yeah, there's a little bubble in there. So it's starting to get a little boiling. More bubbles are building up on the bottom of the boiling flask. The vapors are increasing. The condensation zone is starting to move up a little bit. It was from this thing and now it's on the neck. The sticks, I hear the sticks kindling a little bit. I think that's what's the crackling sound. You might be able to see a little bit of the flames on the bottom. I can see some of the smoke coming off. Oh yeah, it's starting to really go. The fire is definitely up at the sticks. So we know this thing burns wood, and it can burn wood good. You can see more of the fire starting to pour out of it a bit. And you see at the boiling flask how there's more little bubbles. Nothing big yet, but it's starting to increase fast. We're now 3 minutes in. You can see how vigorous the boiling is getting. So this thing can boil water. It's proven now. The titanium cube, pretty resilient to that. Nothing's happening there. If this is boiling water, look how vigorous that is. I might have to take it off soon. Then the sausage must be cooking too, but only time will tell. Look how vigorous that is. That's all from the hexamine. The stick is done burning. It's all like this black charcoal now. It's just the hexamine doing it, and it's pretty vigorous. It's very strong. Almost 5 minutes in. Let's take a little peek on what's going on down here. As you can see, we got quite a nice fire. I can feel the heat through my glove. The rim of the flask is very hot. So we know it boils water, that's confirmed. So we're gonna take this guy off for a little bit and we're gonna put the sausage on full time and see if we can cook that guy, if it has been cooked already. And hopefully it's not an ashen hockey puck. Let's see how our sausage is. Oh, the fire is out too. We burnt pretty much most of it. Hopefully this guy didn't burn. Looks pretty burnt so far. We got a little grease pool. It's a little on the raw side. I wouldn't eat it, but you saw it before, it was pretty pink, and now it's kind of browned. So that's very incredible how it's able to cook that sausage. Let's see if you can cook it a little bit more from the residual heat, but I doubt it. The titanium cube so far. A little bit of some black ink on it. I think it's from the wood or the fire, but that should be easy to clean off. Wow, that cube's pretty hot. It can definitely retain heat, so that's for sure. Let's put a little bit more water on it. If we observe the aftermath, you can clearly see how our sticks are nothing more than brittle pieces of carbon. Pretty much just ash at that point. And our hexamine has been all but used up. Now, hexamine is very soluble in water, but is burnt hexamine the same? It is. After you use your hexamine, it can be very easily cleaned out. It definitely doesn't leave any sort of burnt, hard residue like if you're burning charcoal does. Look at that. Look how much is broken up already. The only thing that's left is a little burnt, pure carbon pieces, really. But for the most part, it's all but been cleaned out. So you can use this thing again and again, and it'll barely leave any stains, other than the wood.